In my previous video, I demoed the first technique that we can use to run EVM Solidity contracts on any CosmWasm chain, our EVM bytecode transpiler that produces CosmWasm-compatible WebAssembly module from EVM bytecode. But the transpiler has some limitations, especially related to emulating the call and create opcodes. So today I will show you another demo of using our EVM interpreter to emulate EVM on CosmWasm, including internal calls to other EVM contracts and factory deployments using the create opcode. So we are using a registry of bytecode, a contract that I wrote in Solidity and transpiled to WasM. And this is actually the factory contract that will create or deploy any Solidity smart contract and then register its EVM runtime bytecode. We will talk more in future videos on why this is necessary for supporting factory contracts, but it is related to the difference between the create opcode in EVM and the instantiate method in CosmWasm. But this EVM registry contract also has another function. It maintains mappings between the CosmWasm addresses, which are 32 bytes, and the equivalent EVM addresses of 20 bytes. The EVM address is derived from the CosmWasm 1 just by taking the last 20 bytes. So whenever we call another contract from Solidity, we always query the registry for the full CosmWasm address in order to emulate the call. So now I have here a local CosmWasm chain, and here I have a dApp connected to that chain through the Kepler wallet. So this is the address for the registry contract and the equivalent hex address. So what we are going to do is go back to our remix, go to the ERC20 contract, and we are going to copy this call data. This contains the deployment bytecode for the ERC20 token and our constructor arguments, and we are going to go to the EVM registry and fill this in the deploy function. And again, I'm going to copy the call data for this, and we are going to paste it here for the execute method, and it's transformed into base 64, and we are going to execute this message. So we are interacting with the registry contract, and what actually happens is a deployment of that code. And I have some prints here just to see what is happening in the background, and you'll see that there are multiple executions and an instantiation. So we'll expect this address to have been deployed for the ERC20 contract. But we can also look at the transaction hash here, and going to the Explorer, we will see the instantiate message, and this is the address that we are expecting. So this is the address of the contract for ERC20. So I have another dApp here, and we are going to put this address for the ERC20 contract here. Now let's also deploy a faucet contract. So this faucet contract uses the ERC20 token. It's deployed with that token's address, and a faucet amount, which is the amount that will be given to anyone who calls this gimme function. So this has two functions, replenish and gimme. And replenish will just call the mint function for the ERC20 token, so the faucet contract gets some ERC20 tokens for itself. And the gimme function just sends some tokens, uses the token transfer function to send some tokens to the message sender, the caller of that transaction. So we need the token address and the faucet amount. So we have the hex address here for the ERC20 token. So we are just going to take the last 20 bytes from this. And now let's make this lowercase so we don't have issues. And the amount that the faucet will give each person who calls it will be 1,000 token units. So let's see. Okay. Now we copy this call data, and again we are going to the EVM registry and setting the bytes here and copying this call data. So we will paste this here. So we will again use it. We will execute the registry contract again and deploy our faucet contract. And we have the transaction. Let's take the new contract address from the events here, and this is the new contract address for the faucet. We are going to paste it here. So the first method that we will call is the replenish method. So let's go to the faucet and see. Copy here the call data for the replenish method. And we are using this directly on the faucet contract, which has been deployed as a standalone contract. And we are doing this with a specialized WebAssembly module that was deployed with code 37. What was already previously deployed, and this is an interpreter. This is an interpreter that consumes the runtime bytecode for the faucet contract that is actually stored in the registry contract. But more on this in future videos. So we are going to interact with the faucet contract and call the replenish method that actually calls the ERC20 token inside it. So we are executing this, and we have already some prints here that I made just because it's hard to see these nested transactions. So we see this is the main execution, and then we have some additional queries here, and then we have the WasmVM VM response handler that catches the internal transaction for minting. So it's another execute method. This is the address for the ERC20 token. For the ERC20 token, and it gives it the mint call data. And this is the execution of the mint internal transaction. So now, if we go back to the ERC20 token, we will try to get the balance of the faucet contract. So let's see, balance of, and we will use, this was the faucet contract address. Of course, it's 0 because we are in remix, but we want the call data from here. So we set this call data here, and we query the ERC20, and it's 0 because this was actually the address for the ERC20 contract. So this is the faucet contract address, And we are going to do the same thing here. Just get the last 20 bytes and then okay, and this is the address that we need, and we should be able to just replace this part here. Okay, and now let's query again, and we have a balance. Let's now see the balance for our address here. So we are going to copy our address and transform it into this EVM hex format, and then so we have a balance of 0 for this ERC20 token. So next we go to the faucet contract and we get the call data for the gimme function. We just need the call data from here. We copy it and we paste it here. Okay, and now we do the execution. So after this works and we see some nested execution functions here, we already got the transaction hash, but let's look again at our balance. And now we have a balance, and this is 1000 in hex format. Exactly what we expected. So you just saw EVM calls being at least partially emulated in CosmWasm. And if we look again at the faucet, you see that these internal transactions don't use their result, because this version only supports calls that you can send without checking the result of the call. Because of how CosmWasm is built to be able to send a call and catch the result and use it. So for example, use this success value, you would need to catch the CosmWasm reply message and be able to continue the rest of the logic with that result. And for this to happen, some more complex techniques need to be used, and maybe we will do that in the future too. What you also saw demonstrated in this video, but you did not see in detail, is that the create opcode is fully emulated. But this in a future video.